Okay, good morning, everyone. I have on the board there what's going on. So today we're going to do series, right? And then on Wednesday we have our exam 3. And I just I looked at the review, but I also was just thinking about what's going to be on that test. Look at the reviews I sent out. Improper integrals. Don't forget, when we covered improper integrals, there were 2 types of improper integrals. And on the last exam, the very last question was the first type. It was infinite intervals, but I did not test you on the other type, which were called infinite integrands. So that will be on this test, probably the very first problem on the test. I'm also going to go sequentially. So when you're taking the test, always keep in mind that it goes in the order we covered everything. So after that, we talked about areas between curves. For that problem, I'll probably have you calculate the actual area, like the entire way, to some numerical answer. From there on, I'm not going to have you actually evaluate any of the integrals. And I'll say it on the instructions. So like on the volumes of solids of revolution, that's one where I'm going to give you a region. I'm going to have you wrap it around different axes. You're just going to be setting up those integrals. You'll be telling me whether or not you're using washers or shells. And then the volumes of cross sections, that's that weird one where you have like some region which forms the base of a solid, and then you're going to look at cross sections that are perpendicular to the x-axis, and those are in the shape of either like a semicircle or an equilateral triangle or a square or something like that, and you have to find a formula for the volume of that solid. So again, that will be a setup only. It will not be a work it out all the way. Arc length and surface area, same thing. I'm going to give you some curves, and you're going to come up with the formulas for arc length, formula for surface area. There is a slight chance that I actually have you compute the arc length, but that will only, like all the way, but that will only be if it turns out to be an easy problem, because some of those can be messy. I'm leaning more towards no, just give me the formula. And then sequences, that's what we did last time. 2 things that will be on there from sequences. I will give you a sequence, right? A list of numbers, and then you have to come up with the formula that generates that sequence. We did some practice of that in class, and there were a few problems on the homework for 8.1 that also cover that. And then the reviews had some problems as well, all right? And then lastly, this again was 8.1. I'll give you a sequence, and you determine if it converges or diverges, and all you do there is take the limit as n goes to infinity. You might need some L'Hopital, things like that. So that's it. That's the test. Now, in terms of what you can have on the test, I've been thinking a lot about this. Like, I know we've talked about it, right? You can, of course, have all your formula sheets that you're allowed that are on our website. But I've given you handouts, right? That nice color handout, right? So I keep going back and forth on how I want to do this. I'm thinking that, what do y'all think about this? I think this is fair, but you tell me. I'm thinking if you want to use that color handout, you're going to have to pay for it. Pay for it in points. So like, in other words, there will be a penalty for using it. Like for me, I don't think that you can make an A on the test if you have to use that. So for me, I think maybe 7-point penalty. Then you can still get an A, but now your chances are reduced quite a bit. What do y'all think? I think that's a fair thing. The difference between an A student and a student who's maybe at the bottom of an A is that they don't need that, right? So that they understand how the solids and the pictures and the outer and inner and all that stuff, right? Sound like a good plan? Yeah, okay, well, it's my choice, right? So I'm trying to sell it to you. So I'll say on this test officially, of course, you can use all the stuff on Canvas formula sheets. If you want to use that color thing I handed out, then the penalty will be at most 7 points. And so what I'll do is I'll walk around. You have to make the decision at the beginning of the test. You can't be halfway through the test and be like, you know what, can I get that sheet now? You make the decision in the beginning, all right? So then I'll walk around and I'll say, okay, and I'll mark your test that you are going to take the penalty but use the formulas. right? Okay, anything else on the test you want to talk about? Y'all feel like you're going to be ready? No? No, not at all? Okay. All right, well, unfortunately, this is one of the most important sections of Chapter 8. This gets us launched off, and there's a ton of stuff here, and I know you're already trying to think about the test, and I realize that when we come back next week, Monday, you're going to probably have forgotten all this, so I'm going to just ask you now that your homework for Wednesday night is to make sure you review what we do today, because you want to have it fresh in your mind when you come in here next Monday, all right? All right, so series. So many notes here. I'm going to be putting them up over there. I'll be writing things on the board. There's a lot of definitions here. Just remember that you have access to all these notes. So don't spend your time trying to copy this all down. The most important thing is for you to understand. I'm sorry I can't project this up front, and you have to turn to see that. Is that big enough? Everybody over here? All right, so series. First, we got to get some preliminary stuff out of the way. Everybody here has to be familiar with what's called sigma notation. So I'm assuming that y'all have seen this at some point, this Greek letter, capital S. Y'all seen that, right? That's sigma? Okay, so in mathematics, we use that sigma to help us condense our notation of things so that we don't have to write long strings of things out. We can use this notation. For example, I have there written 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus ... plus 100. Do you see that I'm just adding up 1 squared plus 2 squared plus 3 squared plus 4 squared? Right? Those are just the sum of the squares. So another way we can write it is this. First, I've realized that there's a formula, n squared, that generates these numbers. Like a sequence, right? Like a sequence. If I were to give you the number 1, 4, 9, 25, 36 as a sequence of numbers, then n squared would be the formula, right? The sigma notation, all it does is it says instead of just listing out the numbers with commas between them, like a sequence, we're going to add the numbers. Why do you think they use capital S? Sum, right? It stands for sum. So we are going to take the sum of what? This formula right here, n squared, we're going to start with n being 1 and stop when we get to 10. So if I start with n being 1, 1 squared is 1. Plus, now I let n go up by 1. Okay, so we call this the index. This index now shifts up to 2, and now 2 squared is 4. We put a 4, and then add to it. Now we let n be 3, and so on and so forth. Make sense? Any questions? So n is the index variable, 1 is the starting of the index, and the 10 is the ending of the index. All right, now, what if that sum goes on forever and ever and ever, right? What if I don't want to stop it? I just want to keep going, ... and don't stop. Then the only thing that changes in this formula is that I put infinity for the top number. All right? You do not have to, you know how on the bottom it says n equals 1? You do not have to say n equals infinity on top, or n equals 10. You can just put a number up there and that's where it stops. All right, good? Sigma notation? Yeah? Okay, next thing, what is a series? All right, so we are going to define what a series is. A series is simply the sum of a sequence. So all of 8.1 was about sequences, right? A sequence is really just a list of numbers, right? And so now what we want to do is add them up. So if we were to take a finite sequence, what does finite sequence mean? There's a finite number of them, right? There's only a certain number of numbers in that list. Do you all agree that if I give you a finite list of numbers and ask you to add them up, you're going to get an answer, right? I mean, no matter what. If I give you 10 numbers, tell you to add them up, you're going to get an answer. If I give you a million numbers, tell you to add them up, you should get an answer, right? So finite sequences always add up to be a finite number. And those are not interesting to us in here. We don't really care about adding up a finite number of things. What we're interested in is adding up an infinite number of things. So we call those infinite series. So an infinite series is the sum of an infinite sequence. Let me say that again. An infinite series is the sum of an infinite sequence. And so this sum, the way we would write it is as follows. There's that sigma notation. I'll try and go a little bigger. I think it's going to be overkill here. Maybe that'll be okay. So this is the notation. This is the general notation right there in blue. That is the general notation for an infinite series. We'd say that sum n equals 1 to infinity of a sub n. That a sub n is that formula that creates the sequence. So we all recognize a sub n as being a sequence from a.1, and then you were just adding them all up. So we would get a1 plus a sub 2, a sub 3, adding all these up, dot, 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 that dot, dot, dot means forever. Now, I'm going to call this sum capital S. Okay? The first question is whether or not this sum makes any sense at all, right? Because if you give me an infinite list of numbers, right, and start adding them up, are you going to get a finite answer? Is it always going to be an infinite answer? Like, this is the question. So a lot of students go into this thinking, well, if I have an infinite number of numbers and I add them up, then my answer is going to be infinite. But that's not the case. You could take something simple like this. Look at this sequence right here. 1, negative 1, 1, negative 1, 1, negative 1, forever. By the way, what's the formula that creates that? Negative 1 raised to the, is it n? It's close to n. We want a positive on the first one. You can do either n plus 1 or n minus 1. What do y'all want? You want to do plus 1? You can do minus 1. You can do plus 3. You can do minus 5. So this is, again, something from last time, right? So this is our formula, right? If you let n be 1, what happens? You get 2 there. Negative 1 squared is 1. If you let n be 2, now you get a 3 up here. Negative 1 cubed is negative 1. So this creates that, right? So what I'm asking is, if I were to take the sum, and my notation is going to be a little different. I'm going to put the n equals 1 below, not out front, and then put infinity on top like that. And then I put this formula in here. The question is, what is it? Well, is this an infinite number of numbers? Yes? Okay. Does it add up to be an infinite thing? No. Right? Because what's happening? If I take this series right here, let me write it out. If I take this series, what I'm doing is 1 plus negative 1, right? Plus 1 plus negative 1 plus 1, right? Plus negative 1. And I'm doing that forever. Do you see that? Like if you just add up the first 2, you get what? 0. And then if I add the first 3, I get 1. The first 4, I get 0, then 1, then 0, then 1. So it looks like as I go to infinity, is it adding up? Well, is it becoming infinite? No. Now, is it becoming a number? It's becoming 2 numbers, right? Depends on where I stop. Do you see that? If I stop at one place, I'm going to get 0. But if I stop the next one out, I get 1. Or I get 0, or I get 1, or I get 0, or I get 1, or I get 0, or I get 1, right? So this is just a first glance into a series where it's not as simple as, oh, all infinite series must be infinite. No, it depends on the series, all right? So that's what I'm saying here. Our first question is, when we take an infinite series, does the sum even make sense? And does it converge? All right, I'm going to get more into this as we proceed. All right, some first examples. Okay, look at that right there. All right, so I give you first the sequence, right? The sequence is a sub n equals n. I think that was the first sequence we ever studied in here, in chapter 8, section 1. A sub n equals n, and that creates the sequence 1, 2, 3, 4, 5, 6, 7, 8, forever, right? So what do you think about that series? What do you think about this sum, S, which is the sum n equals 1 to infinity of n, which just means 1 plus 2 plus 3 forever? Any ideas on whether or not that adds up to be a number, or what do you think? You think it's infinity, right? You think it just keeps getting bigger and bigger and bigger? I think this is an easy argument, don't you? To say, hey, look, there's no way that this goes and gets closer to a number, because every time I add a number, it's a bigger number, and this thing just blows up and gets huge, right? This sum gets infinite. Yeah? Okay, so now I'm not here to settle that yet, all right? I'm just saying, you know, some series, it's kind of obvious that this thing looks like, right, that it's going to infinity, question mark, because I'm not quite sure how I'm going to say that to you, right? Let's look at the next one. I just put here, it's obvious that this sum gets larger and larger and larger. Okay, look at this one. This is the sequence. Okay, so we're doing the series S is sum n equals 1 to infinity of 1 over n, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 forever. What are your thoughts? Do you think this gets bigger and bigger and bigger? Yeah. We could argue. We sit here and argue. I think you can make good arguments both ways. Let me back up for a second. I want to point something out here that I should have and I didn't. Okay. What's the sequence here? What's the sequence? A sub n was n, right? From the 8.1 homework, does this converge or does it diverge? So what do you have to do to answer that question? I'm talking about the sequence. This sequence, does it converge or diverge? What do you have to do to answer that question? It's going to be on your test in 2 days. No one did the homework for 8.1? How do you check for convergence or divergence of a sequence? No? Limit, you take the limit as n goes to infinity of the sequence. What's our sequence? N. So what happens as n goes to infinity here? It becomes infinite, right? This goes to infinity, which means this sequence does what? Diverges. Okay? What would it have to go to for it to converge? Some number, right? Other than infinity is not a number, right? So this is a divergent sequence, isn't it? And as far as the series, it looks like that goes to infinity as well. Do you see that? But these are two different ideas. Here, I'm asking about the convergence or divergence of this sequence. You can tell me that answer just taking a limit. Whether or not those things add up to be a number, that's a totally different question. Let me show you here. Here, what's the sequence? 1 over n. Does that converge or does it diverge? All right, well, let's take the limit as n goes to infinity of the sequence 1 over n. Where does that go? To 0. Okay, so does that converge or diverge? It converges, right? It converges to 0, doesn't it? Okay, now, does the series add up to be a number, or does it become infinite, or what happens? We don't know, do we? Not yet. What is your instinct telling you? What are you thinking? You think it gets bigger and bigger and bigger and bigger? And just like overflows, kind of? Like what's happening each time? Think about it. If I add, let's just start looking at, if I just did the first one, right? I would get 1, wouldn't I? What if I add the first 2? 1 plus a half? 1.5, right? What if I take the first 3? 1 plus a half plus a third? So somewhere around what? This is 1.5, right? What's 1/3 as a decimal? 0.333. So what happens if I add 0.333 to this? 1.833, something like that, forever. And then if I keep doing this, 1 plus a half plus a third plus a fourth, now I'm actually adding up the first 4. Now I'm going to add 0.25 to this, right? Which is going to give me something bigger than 2? Yeah, it's like 2 something. So this right here is, bigger than 2. If I keep doing that, the question is, does this answer, started right 1, 1.5, 1.8, 2, something around 2, those answers as I keep going, does it go to a number or does it become infinitely big? You think it becomes infinitely, what?
Just slowly, yeah.
Wait a minute, say it again.
Really big, just like slower than that does, because it's smaller numbers.
So the numbers are smaller each time, right? So the numbers are going to zero, aren't they? They're headed to zero. They're getting smaller. But what is the sum headed to? That's different. So I don't know if I heard your answer.
It's getting infinitely bigger. Just
the sum's okay. So you're saying the sum is getting bigger, but just really it's getting slowly bigger.
Yeah.
Do y'all buy that? Does anybody think that it gets to some point and never gets past it? So you change it. What are you thinking now?
I don't know exactly, but I want to say like around 5.
Okay, so you're saying
Adding like a little bit, it's gonna like start to plateau.
like plateau out, like asymptotically, like get. Okay, so this is what we have to debate. All right, this is the whole idea behind series: is that if I give you a series, can you tell me whether or not this thing is adding up to and it's headed towards a number, or is it becoming infinite? Or is it like the one we looked at, very first one, where it's just going back and forth between 0 and 1, right? Right? It was 0 if we stopped, and then 1, then 0, then 1, right? So this whole idea is what the next couple of weeks of this class is going to be about. And as you're going to see, it's extremely difficult to answer these questions in general. So we're going to have all these different attacks on how to figure it out. So for right now, I can tell you the answer, but I'm not going to be able to prove it yet, all right? I will tell you that this does become infinite, okay? Very slowly, it does, all right? But that, you're just taking it on faith at this point, all right? Now, let's look at another one. So I just say here, now each term gets smaller, right? Each term gets smaller. Each one of these is getting smaller, right? But what about the sum? Don't know, question. Okay, look at this one. Another sequence to look at. Another series to look at. So I give you this sequence. I'm going to put it underneath here. S is equal to sum n equals 1 to infinity of 1 over n cubed. All right, let's just start plugging in numbers. So 1 over 1 cubed is 1 over 1. 1 over, what's 2 cubed? 8, right? It's all there, right? 1 over 3 cubed is 27. 1 over 4 cubed 64, plus, and I keep going, right? Tell me about the sequence first. Does the sequence converge or diverge? So what's the sequence? A sub n is 1 over n cubed. Does that sequence converge or diverge? It converges to 0, right? So if we do this, if I take the limit as n goes to infinity of 1 over n cubed, this goes to 0. So it converges, right? Well, guess what? This right here is the same thing that you were just saying, right? As we add, they get smaller, right? They get smaller. But these are getting smaller really fast, aren't they? Because these are 1 over n cubed as opposed to 1 over n. So, but it's the same sort of idea in terms of every time we add more, we're adding something, they're just smaller. So you might make the same argument that you made here, right? That, okay, yes, these are getting smaller, but it's going to become infinite, right? Which I told you that's what it does. This one, on the other hand, does not become infinite. This converges. All right, this one actually converges. And to answer the question why is, well, you have to wait, okay? All I'm trying to do is show you right now that if this sequence converges, right? You see the sequence converges on both of these? The convergence of the sequence does not tell you anything about the convergence of the series. It tells you nothing, all right? All right, let's keep going. Now, I have a visual of these. Let me see if I can make this make sense. I want this to fit on here. Not sure how good this is going to look. That's not good. There we go. Okay, so what you're seeing here on the left-hand side is the sequence. And right now we're looking at the first example here, n, okay? So what is this sequence? The sequence is 1, 2, 3, 4, 5, 6, right? That's the sequence. And that's what I've shown you right here. Right here is a plot of the sequence, A sub n. There's 1, then 2, then 3, then 4, then 5, then 6, then 7, right? Over here, what you're doing, this S sub n, what it's doing is it's adding up. It's adding things up. So if I just take the first number here, right, 1, then that would be my first sum, 1. Then I would do 1 plus what? 2. 1 plus 2 is 3, and that's this one. So this is the second sum. What's the third sum? 1 plus 2 plus 3, which is 6. That's this one, right? Then the fourth sum would be 1 plus 2 plus 3 plus 4, which is 10. Do y'all see? That what this is doing is for the number down here is how many of the terms you're adding up. So here I'm adding up the first 4. Here I'm adding up the first 5. Here I'm adding up this first 6. And what you can see is that if I keep doing this, watch what happens to the sum. So I've gone out to the first 100 sums. I've added up the first 100 numbers. And look at, I get 5,050 if I add up the first 100 numbers. But more importantly, look at what this looks like it's doing. What does this look like it's headed towards? Infinity, right? Do y'all understand that the 100th one here, that dot, is adding up the first 100 of those? Right? The 40th one is adding up the first 40 over there. All right, that's what the sequence n is. Now let's look at 1 over n. That was the second one, right? That's that one over there, which we were debating about. What does it do, right? What does this do? So let me show you. We're going to add up. We're going to add up the first few here. Okay, so look at this sequence. The sequence is 1 over n. So it's 1, 1/2, 1/3, 1/4, 1/5, 1/6. See, these are getting smaller, right? And as we add them up, remember the first one means I'm just adding the first one, which is 1. And then the first 2 would be 1 plus 1/2, which is 1 1/2, right? And then the first 3, and then the first 4. Look at this here. Let's go out 100 of them. There's the first 100 of them. It's only added up to be 5 point something, right? So does that curve, you had mentioned asymptotic, right? Does that look asymptotic? I don't know. I mean, you could argue maybe it does, but look, let's go out the first 400 terms. I might slow my computer down here. I need to make the points a little smaller. Yeah, I can't even make them any smaller. So it looks almost like a graph now, doesn't it? So now I've gone the first 400 terms, and look, I'm only at 6.5, right? But look at the graph. Does it look like it's flattening, or does it look like it's still growing? Looks like it's still growing to you, yeah? Well, let me go first 800 terms. Look at that, first 800, I've only grown up to 7 now, right? I've added all the first 800 terms, and they only add up to 7.26245. Understand? Still look at like it's not asymptotic? I've only got this program to go out the first 1,200 terms, so slowed it down a little bit there. Look at that. We've gone out 1,200 terms. We didn't go up by much, did we? Well, what I'm telling you is that, indeed, this thing does become infinite. Okay? So how many terms do you think we'd have to add up to get this to add up to 100? A lot. A lot. Millions, probably a million terms. But it's okay, because we have how many terms to add up? Infinitely many, so it's okay, all right? It's going to happen. Now, let's contrast this. Let's contrast this with, let's go back to 100 here. Okay, let's go to 100. Now let's look at that last one, 1 over n cubed, okay? So take a look. Bring the point size back in here. Look at the sequence, right? The first number is 1, and then it was 1/8, 127. Look how fast that drops, right? See how fast that drops? And look at this sum over here. I'm going to add up the first 100. Here we go. I'm going to make those smaller. Here's the first 400. Here's the first 1,200. Yeah, there we go. Does that look asymptotic to you? It does, right? That looks more like a flat line. And what's happening here, now, how many? Unfortunately, I don't have, I can go further out here. Let me see, hold on. I'm taking up way too much time. It's okay. I'm trying to figure out where I have my rounding here. Okay, so I have it rounding this far out right now, but I can change that so we get another. Let me round that a little further. Okay, there we go. Okay, so let me go back to n cubed. Make this one a little smaller. There, that's good enough. So I'm doing n cubed. Look at this number right here, okay? Right now, I'm adding up. I'm going to start adding up the first 1,200 terms. Watch that number. Shit, what happened? Okay, I want this smaller. I don't know if this is going to work. This smaller. Let me just show you. Okay, n cubed. Look at that number 1.19. I'm going to go out the first 1,200 terms. That's the same thing, isn't it? Didn't fix it, did it? Okay. We move on. It's not changing, right? 1.2 something, right? 1.2 something. Now, but you have to understand here. Do you agree that if I stopped at the 1,200th term, I've added up the first 1,200. Do you all agree that if I do the next one, if I add the next one, that number's going to go up a little bit? Right? A little bit. But we're talking decimal points way, way, way out there. And it's not going to have an impact on the fact that it's never going to get past 1.2. All right? Okay, let's just keep moving. The main thing here is for you to understand that series behave weird, all right? We have to investigate further. All right, so now the big challenge is me just summarizing what I just said. The big challenge is to see whether or not a series converges to a number or not. But we cannot just tell by looking. So this is the hard part of what this is all about here. So in order to help us figure out if a series converges or not, we're going to use these things called the series tests. And there is an actual sheet in your formula sheets that there's all these, it's something that's been on Canvas since day one of this class. And that sheet I would start bringing to class now. Someone have it? I can hold it up. See if anyone has it. That's it. Okay, it looks like a table. Okay, has a couple of columns and a bunch of tests. These are the series tests that we're going to have to use. Right, so for each series we see, we're going to see which test